Hello, everyone. Have you all been enjoying the conference so far? Nice. So just before we start, I wanted to get a quick vibe check. How many of you here have played with reasoning models, like O1? So yeah, just about everyone in the room. That's perfect. How many of you have worked on training reasoning models? Oh, that's surprising. No one. But we'll change that maybe by the end of this session. As Naveed mentioned, I have a book. I also have 3 copies to give away. They will be to people who ask me, the most insightful questions that either confound me, befuddle me, or blow my mind away. Need not be mutually exclusive. So yeah, but let's get down to business. How does one make a SOTA language model? Let's say we get $1 billion assigned to this room, and we are asked, can we beat the best? What can we do about it? So there are so many different axes along which we can make improvements. Maybe you can change the model architecture. Maybe it's a diffusion model. Maybe you change the attention mechanism and innovate something there. Maybe better training dynamics, that's like better optimization algorithms, or even learning objectives, or tokenization strategies. As we all know, subword tokenization is the worst of both worlds. Or just higher quality training data being more sample efficient. And you can see just brute force scaling the data size, the model size, the compute, etc. But there's one more axis that has been driving almost all of the improvements, not almost all, but especially at the higher end. And that is scaling text time compute, which is making the model compute for more time before generating an answer. And this, when GPT 4.5 came into the scene, I think the OpenAI people had a podcast where they showed that they are now actually data constrained and not compute constrained. And that means that pre-training is slowly starting to get diminishing returns. Obviously, there's a lot of data available in the world that has not been made into a pre-training data set, but it's also about quality of data and about the marginal returns you get from particular data samples. So what exactly is the motivation behind inference time compute? So from cognitive sciences, we have this system 1, system 2. I'm not a cognitive scientist. I don't know how well the analogy holds, but this is how people describe it. System 1 is traditional language models, fast, perceptive, unconscious. You ask it, you give it a prompt, it starts generating right away. System 2, however, is more methodological. You put in thought and effort before giving an answer. And that is kind of expected, right? Because in computer science, you have this computational complexity. Some problems are more difficult than others, and they are dependent on the size of the input length. But in LLMs, regardless of what you give it, it's constant time computation. So system 2 makes sense, and that's what the scaling has been going on. So a lot of people have been exploring this question. A few years ago, it was the big hot discussion topic was, do LLMs really understand? Because if you have a particular definition of understanding, and then you can see that, oh, LLMs actually do not understand because they don't do X, Y, Z. In my opinion, so do we really need LLMs to understand exactly the way humans do, especially if they are giving us the outcomes that we want? So I think it is a very, for intellectual curiosity, it's a really interesting question to know if LLMs understand. And right now in 2025, the thing is, do LLMs really reason, and whether they reason or not? So do we really care? I mean, yes, but maybe not as much as we should, is my hot take. So everyone might have heard about this paper called The Illusion of Thinking that came out by Apple. As you know, maybe a quick show of hands. How many of you have heard of this paper? Oh, wow, everyone. So it's so popular. Okay, and it just came out a week ago. So a lot of mainstream media outlets took this as an opportunity to say, yes, LLMs don't know how to think, etc. I personally have some disagreements with what they have come up with, but here are things that I actually found very convincing. The first part is that AIM is there. That's the mathematics exam, which is combinatorics and number theory and a few other very hard questions that are like the precursor to Olympiads. So AIM 25, the performance is worse with all the reasoning models than AIM 24, even if humans are saying that it's actually easier. And that's happening because of benchmark contamination. And this is actually, you can see it for many different data sets. The newest version, the models just do worse, and that's because there is some amount of contamination. But then the question is actually how much, it's not really that big a gap. So the model is still probably doing so-called reasoning. And then the other thing that they found was reasoning collapse is observed at problems with higher complexity. So the paper, as you know, experimented with these four things like towers of Hanoi, checker jumping, blocks world, river crossing. So by the way, we have the world's foremost checker jumping expert in the hall right now. Can you quickly say what exactly is checker jumping?
Sure. By the way, how many of people here know what checker jumping is? Okay, cool. Then I can say anything. No. So in checkers jumping, the goal is to capture all of your opponent's pieces, and it's a board game. And the way that you do it is by diagonally jumping over the pieces and of opponent's pieces. And once you jump over, you capture your opponent's piece and you remove from the board.
So whoever wins a game against checker jumping, him gets a copy of the book. No, just kidding, just kidding. Okay, so what is the most interesting part that you see here? Can you see the green and the red? I think you don't see it. That's sad. Can anyone? You can see it? Okay, I can't, but okay, if you can, then it's great. So you can see that at n equals 1. So that means when it's one disk for the tower of Hanoi problem. So that means when the problem complexity is low, it's getting it right as soon as it starts thinking. But when it thinks more, it overshoots and starts getting it wrong. But if you see at n equals 5, etc., its first tries are wrong, and then it goes to a correct solution. And then at n equals 10, n equals 15, etc., it's like, it just doesn't get it at all. So what, by the way, the reference at the bottom is wrong, so disregard it. But here are some takedowns on the illusion of thinking. Some of them I think I saw in the internet. Some of them I think it just came to me while I was analyzing the paper. So there's a conflation between cannot solve and chose not to exhaustively solve. So in the evaluation of that particular paper, you just because sometimes the model says, okay, I solved it for cases 1, 2, 3, 4, 5, and here is how I will do it for the rest, but it's not actually going to enumerate it exhaustively, and that should not be seen as a case of not being able to solve. So the reasoning collapse in the Tower of Hanoi problem, at least, apparently is happening due to the output length constraint. And there is also this thing that models are trained such that they know when they are reaching the end of the output limit. The other thing is that for any problem, you can always find an input representation that for which the model just doesn't work, or vice versa. And for blocks world, etc., Subbarao Kambhampati from Arizona State University, you can watch his videos on YouTube or his papers. He has done a lot of experiments with the blocks world, and they show that yes, LLMs are not really, they are not, they can't solve these specific tasks, even though there might be a semblance of reasoning happening everywhere. And then evaluating on output. So this is like a net. In the Apple paper, they were using a temperature of 0.7, and then they were like, the way they were evaluating was very strict. It just doesn't work. And then finally, the thing about what makes a problem complex. If in the tower of NI, is it in the number of disks? But if a problem has linear time solution, does that even matter? Or you have to look at the branching factor. But that's all for humans. What does complexity mean for LLMs? That's something we don't know yet. Let's now talk about how we are going to do test time compute, scale test time compute for reasoning. You can either do parallel or sequential or a mixture of both, hybrid. And parallel is just generate n solutions and select the best one. Sequential is just go by one path and then try to backtrack, try to verify, backtrack, and so on until you reach the final answer. You can also scale across multiple things. So you can divide a problem into multiple steps, and then you can scale parallelly at a single step. So for example, for each step, you can generate n solutions, and then, or you can do it at the solution level. The other scaling dimension is test time training. So you can, at test time, you can collect, the model can collect training data for that particular task, fine tune the model, or in context learning scaling, which is scaling massively the number of few short examples in the prompt. So scaling test time compute works regardless of what that Apple paper said. So you can see here that as the number of tokens increases, in this seminal paper, as one simple test time scaling, you can see that it's increasing. And even if you have tried on your own any difficult logical reasoning task, etc., and you ask it to think longer, it just gets better. Parallel scaling, how do we implement it? Best of n usually, or self-consistency, which is a very nice way of saying, not a very nice way, but a very convoluted way of saying majority voting, probably. But I think many of you, or all of you, know what self-consistency is, weighted self-consistency. Promising factor here is you can, for the best of n, you can use a very ensemble of models or a lot of small models and so on. So you can mix and match and and scaling parallelly, you can scale to 80,000 or 100,000 solutions, and there's a chance that one of them is the right answer. All you need to have is a good verifier model. So in cases where you have a good way to verify, parallel scaling is great. So as of, how do you do best of n? You use a reward model for scoring, and then choose the one with the highest reward, or you use LLM as a judge, or you use confidence measures. The third one I'm going to speak about a little more in a few minutes, where you select the answer that the LLM is most confident about. However, the confidence, the model needs to be calibrated. That means the model should not be overconfident about its own skills, etc. So we'll talk about that quickly in a while. Sequential scaling, yes, as you see, LLM as a judge or external verifiers could be heuristics and whatnot. The problem with the sequential scaling is that you need large context windows. Let's say you are, backtracking and you are, verifying, coming back, etc. Your context, the size of the context window just expands, and you need smart context management. Hybrid scaling, I'll skip over this. It's just mix and match. You can mix parallel and sequential any way you want. Okay, so now we can go to scaling pitfalls. And we have overthinking. That's when the model thinks too much than we need to. There's just this wasting tokens, or underthinking where it doesn't think enough. Hitting context length limitations, difficulty in asserting confidence. We have our resident overthinking expert. No, just kidding. There's no one here, but I wish there were. But this is something that you may have all seen here, right? What is 55 plus 34? And you ask a LLM this with a reasoning model, and it got the right answer very soon, like in the second paragraph, but it continues to verify that is correct. And then at the end, it uses a whole lot of tokens for just verifying, because it could have stopped at the end of the second paragraph, but it's not. So, so this is a phenomenon, the overthinking phenomenon. So what can we do about it? There's this nascent field of thought budgeting, something I've been working on for actually kind of over a year or so. And it's, how do you control the length that the model is reasoning for? So one of the simplest ways, and that is from the S1 test time scaling paper, is to use these step indicator tokens. So if you look, I don't know how to go back, but if you had memorized the reasoning, oh, okay, it went back. So you can see that it's using the word so this is DeepSeek R1, and it's using the word alternatively, and that is kind of a token that it uses to go to the next step of the reasoning process. And different models have different kind of these step indicator function, tokens. So what you do is, if you want the model to think more, you just insert this alternatively, or maybe, or but, and then you are forcing it to think more. And then if you want it to stop thinking, you can insert end of thought, like the thought end of thought token, or the final answer is. How does this look? So this is an example. You can see that it gets the wrong answer after the 4th bullet point, but then you can put wait, and it continues thinking again. And then you are like, okay, this is enough. We can put final answer, and so on. So what's the problem here? The problem is that the way this works is you set a budget, and then if the model thinks less, you make it think more. If the model thinks more, you stop. More than the budget, you stop. But how do you set the budget? You don't know how to set the budget ahead of time. And you don't know which problems need what budget. So it's not really a very useful technique. Also, the problem is that increasing reasoning lengths can lead the model to go into repetitive loops. So what that means is that it thinks, but it's just repetitively thinking the same thing. So it's not going to be doing anything novel. How do you prevent repetitive loops? Use the frequency penalty, so it's not generating the similar tokens, or change the sampling temperature and make it more creative, and so on. The next way to control this is using fine-tuning. And the way you do it is you want to optimize for certain prompts, and the certain prompts are like, let's say it could be think for 2,000 tokens, think for 6 steps, or think really hard. And then you fine-tune the model with the data set. And the data set has these kind of prompts, along with the reasoning traces that are compatible with these prompts. One thing that it worked in my experiments is the think for 6 steps. It's actually coming from the S1 paper, where they report that they weren't able to work, but it actually worked for me. And that is like, in the reasoning trace, you have something like think for 6, step number 1, 5 steps remaining, step number 2, 4 steps remaining, and so on. And so why is this happening? Why do we want this? Because if you say think for 2,000 tokens, the model is not good at counting the number of tokens. It can't count the number of tokens. You can't control it that way, but you can control it with the number of reasoning steps, because you can make it count down, say 3 steps remaining, 2 steps remaining, 1 step remaining, and then you can stop at 0. Think really, really hard. So that is how OpenAI has it. It's medium, high, and low parameters. So they have these 3 settings, and that's how they provide their models. So what we really need is this. There's a really good paper, Difficulty Adaptive Slow Thinking for Large Language Models. It's fine-tuning for thought budgeting. So what you do, this is dynamically the budget changes as per the difficulty of the problem. And how do you do this? You use the accuracy of the model for a particular question. This is during the training, as a proxy for how much thought you need. So P here is the proportion of samples with the correct answer. So that means you are sampling n times, n solutions, and you're seeing what percentage of them are correct. And then you have a L max, which is your budget, your maximum budget. And then based on, so what happens here if P is 0, you are doing L max. So that means P is 0, the model doesn't know how to solve the problem. So you want it to think as much as you want. You think like to the maximum limit. But if the model is getting it 100% of the time, then you just think the average thought length. And yeah, the way it works is using this reward function for correct answers during the reinforcement learning stage. If the length crosses a particular budget, the reward will be decayed. If the length is below the budget, then the reward will be enhanced. Or for incorrect answers, if the length is below the budget, the reward will be decayed. And if the length hits the budget, then the reward is saturated. So the real bitter truth is that no amount of post-training can vastly improve a weak-based model. So you can't take a random model like the much panned Llama 4 and then build the world's best reasoning model with it. You need a really good base reasoning model. That's why a lot of the experiments in this field use Qwen32B, which is like really very solid or top of the class base model for its size to do its reasoning experiments on, because post-training is not imparting it, or at least that's what we are noticing, new capabilities, but they are just activating the capabilities that were imparted during pre-training. So how many examples do you need? So you can, there are these papers from a few years ago. Lima said 1,000 examples is all you need, and the S1 says 1,000 examples is all you need. Is this true? Yes, it is. But the bitter truth is it takes a lot of experimentation to generate those 1,000 efficient training samples. So you start off with a very large set, and then you do ablation studies, or you use all kinds of filters to bring it down. And I was trying this, and then I was like, I could have just, the effort involved in bringing the size of the data set down was a lot more than whatever I saved by training on a smaller data set. So yeah, it takes we don't know, there is no, what do you call it? There is no algorithm or a set of rules really to build the best training examples. We don't know that. But however, there can be tips. The first bullet point is wrong. It should be long examples. How many thought tokens does the base model take to come to an answer? Difficult examples. How easy is this example for comparative models? Synthetic data is probably a must, because reasoning traces it's very hard to write down a reasoning trace manually. So you need really diverse seed examples in order for the synthetic data to be actually pretty useful. And then also, try at my company, we have domain experts who cost a lot of, unfortunately, but that means that the data set generation process takes a lot of time and effort and resources and so on, but it's still worth it, because they are the only ones who are actually able to generate the domain-specific reasoning traces. Weak to strong generalization for many tasks. As I said, it's easier to verify the answer than generate it. So here is where the weak to strong generalization is seen in all its beauty. Use smaller critic models to verify and provide feedback so that you improve a larger model. So that's how you do it. So we talked about overthinking so far. The next thing is underthinking. What if it thinks less? It's called the shallow hopping problem. The model starts a train of thought, but then it stops. It stops a train of thought and starts thinking something else. Again, I use the words thinking colloquially. So so that's the shallow hopping problem tendency. I haven't seen many good works in this area. I mean, you can just train it to think longer, like doing this, like a DPO, where you have the positive example as something that is thinking for longer, and the negative one as something that's thinking for shorter. And then you train it, you just train to think for a longer time. So the next issue, as we mentioned, was about managing a context window. So sequential scaling needs very large context windows. So what can we do about that? There are a few techniques that are proposed. Some of them have worked for us. This one, so you can see there is the initial prompt, C, the thoughts, and then for each step, you have the thoughts, T, the answer of the current step, A, and then you reduce it by removing the thoughts. And here what's happening is, unlike the DeepSeek example you saw, at the end of each thought step, you output the answer for that step. Because usually what happens is they think for many steps and then they output the answer right away, like the entire answer. But here you like output the answer for that particular step and retain only that answer, but remove the thought. The other way to do it is summarization, where you have C, T, and then you have the summary of the thought tokens. And then you can see that it's reduced in the next step to see the history from the previous steps, and then the new thought, and then the new summary. And then the S-1 is just getting replaced with the new summary, etc. And that's one way of dynamically managing context. I have found this very hard to work with because summarization, it's not easy to, even though summarization is the most low-hanging fruit use case that many people say, getting actually good summaries is very hard because you don't know what you are supposed to concentrate on. And then you can do it as Markov processes, where you treat it as a directed graph. Nodes with no incoming edges are independent questions, and then you make it so that there are these blocks where each block is just whatever the dependencies are there for that particular node. The problem, again, with all these techniques, it's not easy to identify which part of the reasoning sequence are important to the model. As we all know, thought traces are not faithful. So that means that you can have the model showing its reasoning trace, thinking about something, maybe a wrong thought, but it gets the right answer, or vice versa. So the reasoning thought traces are just not useful for anything. I mean, for interpretability. They are at best a source of entertainment. Okay, so I don't have time to do the very last section, but I can say this. One aspect of test time scaling is that it improves confidence in a model. So one way that you can use confidence is by using a confidence threshold to determine whether you should say I don't know, because that's one of the biggest issues. And I know there are people here who are here for this talk just because they want to know if there's anything you can do about hallucinations. And here, the idea is that if you are not confident enough, you just say, I don't know the answer. In the model prompts, I don't know the answer. And that's one of the ways that use this. Okay, so does this include the time for the questions?
Yes.
Oh, okay. So I have only 1 minute for the questions, unfortunately.
So yeah, I guess we have time for a question or two, depending on the question. Who is the mic runner for the, okay.
Thank you for a great talk. So the question with Tower Hanoi, if you take an intelligent child and don't ask them to solve the problem, but explain to them the solution, right, an abstract solution, they'll be able to solve it for any n,
yes.
right?
Yes.
So, and then, so the question about slow and fast thinking, slow thinking is abstract first, it's deliberate second, but abstract first.
Yes.
And an abstract explanation of Tower of Hanoi has gotta be in the training set, because it's like literally every book describes it.
Yes.
Why do you think LLMs, or do you think that is the proof that LLMs do not behave, they don't do abstract thinking, the fact that their behavior on a different end is different?
That's a really good question. So for towers of Hanoi specifically, I tried that later, the same thing that was in the Apple paper. I saw that it was actually able to do it if you have longer output lengths. So towers of Hanoi specifically, even as the number of disks grows, just because there is a formula, a way to, yeah, it is actually able to do it. But with the other games that you saw, it was not. So as the problem complexity went, and even though there is, I think, a solution, yeah, I think it's unknown right now. I think we don't know yet what is happening, because for some games, I can see that they are able to internalize the algorithm and figure out for cases where n equals arbitrary number. But there are other games where the same exists, but they don't. So we don't know exactly why. And maybe it could be because Tower of Hanoi is a very popular game, and it has been in the training set tens of thousands of times. That could be a